Naresh, working as assistant professor in AC department. And today's topic is question bank discussion on module 2, that is bipolar junction transistor. So, in this session, we'll discuss a part A and a part B questions from the module 2. So, in the first question is a transistor has IB is 100 microamperes and IC is 2 milliamperes. Solve beta of the transistor, alpha of the transistor, emitter current IE, and if IB changes by plus 25 milliamperes and IC changes by 0.6 milliamperes, find the new value of beta. So for this case, first you need to calculate this beta and alpha. So from this case, we have that IB and IC. So from this, if you know this from the common emitter configuration, so base terminal is acts as the input and collector is acts as the output. From that, we can define the beta is the DC current gain is, it is a ratio of output current to the input current. So here the output current is IC and IB is input current is IB. So hence you can substitute IC value is 2 milliamperes, that is 2 into the power of minus 3, and IB is 100 microamperes, means 100 into 10 to the power of minus 6. So by using this one, first solve this beta. Then the second one, we need to calculate alpha of the transistor, means we know that alpha. So by using this one, we observe this beta. Then we need to write this alpha in terms of beta. So we know that alpha is equal to beta by 1 plus beta, means this value can substitute then to observe the alpha value. Then the third case, for this case, so we know that IE is equal to the summation of base current as well as the collector current. So hence, we know that IB is 100 microamperes, 100 into 10 to the power minus 6 plus IC is 2 milliamperes, 2 into 10 to the power of minus 3. So means this is 0.1 into 10 to the power of minus 3. Then this is 2 into 10 to the power of minus 3, hence 2.1 milliamperes. Then after that, the fourth one, how to solve this fourth one? If IB changes by plus 25 milliamperes, means, so the initial IB value is 100 microamperes. Now it changes to 25 milliamperes, means the delta IB is represented as IB1 plus IB2. So here the IB1 is the old base current, that is 100 into 10 to the power of minus 6. Now this is 25, new value is 25 into 10 to the power of minus 3. That is the delta IB. Similarly, the delta IC, where the delta IC changes to 0.6, means, so means we need to write IC1 plus IC2. So the old IC1 value is 2 milliamperes, 2 into 10 to the power of minus 3, plus new value is 0.6 into 10 to the power minus 3. Then you can calculate this new beta. Beta is equal to the dou IC by dou IB. So by using this one, you can calculate like this for this problem. Now the second one, solve the base, collector and solve the base, collector and emitter currents and VCE for the common emitter circuit shown in below figure. For this case, the given specifications are VCC is a 10 volts and the VBB is a 4 volts. RB is a 200 kilo ohms, meaning this is the base resistance is 200 kilo ohms, and the collector resistance is 2 kilo ohms. And in between this base and the emitter, the given that is VBE, means the transistor on potential voltage is 0.7 volts and the DC current again is represented as 200. Now we need to calculate. So by using this figure and the given specifications, we need to calculate IB and IC as well as I. So from the circuit, if you want to find out this IB, so means we need to write this one, the potential difference. So this is the source, means IB is equal to VBB minus another voltage source between base and emitter, that is represented as VBE on by so RB. So you can substitute. So in this case, the VBB value is 4 volts. Hence, so here I substitute this is VBB value is 4, and the VB in the problem is given at 0.7 divided by RB value is 200 kilo ohms. Then we observe this, the base current is 16.5 microamperes. And again, from the transistor, we know that IC is equal to beta times of IB plus 1 plus beta times of IC naught or ICBO. And where IC naught is a reverse saturation current, if you neglect that, IC is approximately equal to beta times of IB. So hence, in a given problem specifications, the beta value is a 200. So hence, beta, when substitute the beta value, and IB we observe that is 16.5 microamperes, hence 200 into 16.5 into 10 to the power of minus 6, then it gives a 3.3 milliamperes. Then we need to calculate the emitter current. So emitter current means, so the summation of base current and the collector current. So IB we observed and IC observed, just you can add these two to get the total emitter current, that is 3.3165 milliamperes. Again, in the problem, so we need to calculate VCE. So to observe this VCE, apply the KVL here. So hence, to write this one, VCC is equal to IC times of RC plus the potential difference between this collector and the emitter is represented as VC. So hence, that is VC. So from this, the VC is equal to VCC minus IC times of RC. Now I am going to use this same formula. VC is equal to VCC minus IC times of RC. In a given problem, VCC is represented as 10 volts, hence 10 minus IC value we observed that 3.3 milliamperes. And in the problem again, RC value is 2 kilo ohms. So hence substitute these values. Then to observe this VCE is 3.4 volts. Now, the next question. In a common base connection, the emitter current is, means the IE value is 6.28 milliamperes and the collector current is 6.2 milliamperes. Now we need to estimate alpha, beta, and gamma. So we know that in CB common base, the collector is acts as a output terminal and the emitter is acts as a input. Means if you want to define this alpha is represented as, it is a ratio of output current to the input current, that is IC by IE. So hence, first to identify this alpha is equal to IC by IE. So in a given problem, IC, they are specifying as 6.2 milliamperes and the emitter current is 6.28 milliamperes. By solve this ratio, then you can observe this alpha value. Then now, so if we want to find out this beta in terms of alpha, we have one relation between alpha, beta, and the gamma. Beta is represented as alpha by 1 minus alpha. Then you can substitute this alpha value. Then you can observe the beta. Then gamma means either this is 1 by 1 plus this is 1 by 1 minus alpha, or you can also write 1 plus beta. You can substitute anything, then it is defined as a gamma. So means based on this, you can calculate alpha, beta as well as the gamma parameter with respect to this given specifications. The next question is, The reverse leakage current of the transistor when connected in CB configuration, that is 0.2 microamperes, and it is 18 microamperes when the same transistor is connected in CE configuration. So now we need to solve alpha and beta of the transistor. And in generally, we know that the standard relation is IC is equal to beta times of IB plus 1 plus beta times of ICBO. So means this is represented as ICO, IC or IC naught, and means this is nothing but a reverse saturation current. That is means so 1 plus beta times of, so this is ICBO, that is equal to then your reverse saturation current when writing like this means, so then this is given as so we need to calculate in this the reverse saturation current is connected in a common configuration, that is given as 0.2 microamperes. So that is the reason this is 1 plus beta times of 0.2 into 10 to the power of minus 6, that is equal to ICU means when common emitter configuration, that is the reverse saturation current, that is 18 microamperes means. So this is 18 into 10 to the power of minus 6. Now you can calculate this 1 plus beta is equal to 18 into 10 to the power of minus 6 by 0.2 into 10 to the power of minus 6. Now here we need to calculate beta value. So beta is equal to this 10 power minus 6 is the get cancel. So means this is 90 minus 1. So hence beta is equal to 89. Yeah. Then similarly, we need to calculate alpha value. So means alpha in terms of beta means alpha is equal to beta by 1 plus beta. So we observed beta value is 89, hence 89 divided by 1 plus 89. Then you can solve this ratio, it gives the alpha value. Now another problem is a transistor operating in CP configuration has IC is equal to 2.98 milliamperes, means the collector current is 2.98 milliamperes. IE is 3 milliamperes and IC naught, that is 0.01 milliamperes. Solve which current will flow in the collector circuit of this transistor when the connected in CE configuration with when this transistor connected in CE configuration with a base current of 30 microamperes. So based on this, we need to find out how much collector current is the flows. So when this current will flow in the collector circuit of this transistor, and based on the given specifications here. So from the common base configuration, so we know that IC is equal to alpha times of IE plus IC naught. So therefore, from this, so we are calculating this alpha. So what is alpha value? IC minus IC naught by I. So in a given problem, IC is given as 2.98 milliamperes and IC naught is 0.01 milliamp. So hence 2.98 minus 0.01 divided by the total emitter current is given as 3. So in a problem specification, IE is 3 milliamperes. So hence this is 3 milliamperes. Then we can solve this one. We give that alpha is 0.9. Now we know that when relation beta in terms of alpha, that is alpha by 1 minus alpha. So hence 0.99. So this is 0.99 divided by 1 minus 0.98, that is equal to 99. Then for CE configuration, this is for CB configuration. So similarly, we need to calculate for CE configuration. So in CE, we know that IC is equal to beta times of IB plus 1 plus beta times of IC. So beta is 99. So then IB value is, we observe that IB is in that the base configuration, the base current is given as 30 microamperes. So hence here I substitute this one, the base current is IB value is 30 microamperes plus 1 plus beta times of IC naught. Then it gives the CE configuration. The collector current flows in the circuit, that is 3.97 milliamperes. Now, the other problem is a certain transistor has the DC current gain, that is alpha of 0.98, and a collector leakage current IC naught of 25 microamperes. Find the collector and the base currents when IE is 2 milliamperes. So means in a given problem, given that alpha is a 0.98 and the collector leakage current is IC naught is 25 microamperes. Now we need to calculate base collector and base currents. So we know that the collector current, so with the given that the DC current again is a 0.98, hence the transistor is configured in CB. So in a CB, just now we observe that IC is equal to alpha times of IE plus IC naught. So that is represented as this. In the previous case, we observed like this in a common base configuration. IC is equal to alpha times of IE plus IC naught. So here now alpha value is 0.98. IC value is 0. Alpha value is 0.98, and IE is 2 milliamperes, 2 into 10 to the power of minus 3 plus the reverse saturation current, that is IC naught is 25 microamperes, means 25 into 10 to the power of minus 6. Now can solve this ratio, it gives the IC. Now we need to calculate the base current again, IB. So means from the transistor construction, we know that IE is equal to the summation of base current and collector current. So in a given problem, IE is a known parameter. This is IE is a known parameter. IC just now we got. So hence from this relation, we need to calculate IB is equal to IE minus IC. So now substitute this IE value. So IE value is a 2 milliamperes and IC value this is. You can substitute here and then you can observe the IB value. Now another problem, in the transistor amplifier shown in below figure, the collector resistance RC is 8 kilo ohms and the load resistance is 24 kilo ohms and the VCC is 24 volts. Draw the DC load line and determine the optimum operating point and also draw the AC load line. So for this case, first we need to identify the DC load line. So we know that the DC load line means we need to calculate a VCE Q point, VCE. So we know that VCE is approximately equal to VCC, and to find out this maximum collector current, that is IC is equal to VCC by RC. So then if you want to define this Q point, the half of the center of the DC load line is defines the operating point. So hence first we need to calculate the DC load line. To observe this DC load line, so we need to observe when the collector current is 0, the VCE becomes to VCC. When a VCE is 0, then the collector current is represented as VCC by RC. So hence here I am going to identify from the circuit. So we know that uh, so based on the given circuit, to write down this input side loop means VCC is equal to, so from that circuit VCC is equal to IC times of RC plus VCE. Hence from this we can calculate VC is equal to VCC minus IC times of RC. Then now substitute these values, then we get so just what we discussed now. To identify the DC value, VC is approximately equal to VCC and IC is equal to VCC by RC. Hence, so we know that the given value is VCC voltage is the 24 volts, hence VC is the 24 volt. And now similarly, we need to calculate IC. IC is equal to VCC by RC, means so 24 by the RC value is so in the given case, what is the RC value? So RC value is 8 kilo ohms. So hence, so hence 24 by 8 kilo ohms, 8 into 10 power 3 means 3 milliamperes. Hence, the collector current is IC is the 3 milliamperes. Then we know that now we need to find out the optimum operating point, and based on the concepts of DC load line analysis, the or in a transistor for active region, to satisfy the amplifier condition, the operating point should be always the center of the DC load line and there should be an active region. So hence we need to find out the optimum Q point. The Q point is a functioning of VCE and IC. So just now we observed that the VCE value is 24 volts and the IC we observed the 3 milliamperes. Hence to find out this Q point means VCEQ and ICQ. So what is the VCEQ? That is half of the DC load line, that is VCC. And here this is again half of the DC load line point IC. So hence VCC value we observe that is half of the VCE value and this is half of the IC value. So means 24 by 2, that is equal to 12 volts, and here this is 3 into 10 power minus 3 by 2, that becomes 1.5 milliamp. So these two are indicates the operating point. Then we need to find out the AC load line. So we need to find out, in the presence of AC signal, we need to find out what is the maximum VCE and what is the minimum IC. So based on that, when a AC signal is presented for a given circuit, the load resistance is connected to across the capacitor, and based on that we know that the total output resistance is a parallel combination of the collector resistance and load resistance. Hence, so based on the given specifications, we know that the collector resistance is 8 kilo ohms and the load resistance is 24 kilo ohms. Now the parallel combination of this value is equal to RAC, means RAC equal to RC parallel with RL, means 8 into 10 power 3 into 24 into 10 power 3 divided by 8 plus 24 into 10 power minus 10 power 3. So that is kilo ohms. Now we can solve this one. It gives that RAC value is 6 kilo ohms. Now we need to find out the maximum VCE point, that is VCEQ plus ICQ into RAC, means VCEQ we observe the 12 volts, ICQ is 1.5 into 10 to the power of minus 3, and RAC we observe that 6 kilo ohms. Hence, so this is 6 into 10 to the power of 3. This 10 power 3, 10 power minus 3 is a get cancel. Then you can solve this one. It gives that maximum VCE is 21 volts. Similar to that, we need to calculate IC, maximum IC. So hence that is ICQ plus VCEQ by RAC, means this is 1.5 into 10 power minus 3 plus VCQ is a 12 by RAC is a 6 kilo ohm 6 into 10 power 3. Then by solving this ratio, it gives the maximum IC value is 3.5 milliamperes. So based on that, we need to draw the DC load line and the AC load line, and these two load lines should be absorbed with the output characteristics. Hence, for the transistor, the output characteristics are drawn between the output voltage and output current. So here I consider that a combinatorial configuration. So in that, the output voltage is represented as VCE, and output current is represented as collector current. So we observe that the VCE value is a 24 volts and IC value is a 3.5 milliohms. Then IC value is a 3 milliamperes. And this intersecting of these two, A node and the B node, the intersecting of A node to B node, that indicates that node A to node B, it indicates a DC load line. Indicates the DC load. Then we observe the Q point. So what we observe in the Q point? The Q point is located at the center of the DC load line. Hence, the ICQ we have that 1.5 milliamperes, and VCQ we observe the 12 volts. So hence, we located this 1.5 milliamperes and the 12 volts, that is intersecting point. It defines the Q point. Then after that, we need to draw the AC load line. So means maximum VC we observe the 21 volts. The collector current is observed the 3 point. The intersecting of the C node and the D node is nothing but AC load line. Let's see another problem. So the collector current shown in below figure, given Q point values are to be ICQ is 1 milliampere and the VCQ is 6 volts. Assume that the VCC is 10 volts, beta is 100, and the VBE means, and that emitter base has a forward bias. That means the conduction state across the PN junction is 0.7 volts. Now for this case, we need to calculate the collector current based on the given specifications. So for this case, first I'm going to calculate this RC. So then we need to apply the KVL at the output side, and internally the potential difference between these 2 points, that is represented as VC, is set. So hence the one voltage source is the VCC and the voltage source VCE is set. The potential between these two is represented as VCC minus VCQ by ICQ. So then we know that VCC is 10 volts, VCQ is 6 volts, and then so the RC value, now we need to value the RC value, means ICQ, we need to observe this ICQ means. So hence the ICQ point, that is given that 1 milliampere. So hence, so you substitute this one, VCC value is 10, VCQ is 6, and ICQ. Then you can observe this RC, means that is the collector resistance is 4 kilo ohms. Then from this, now we need to calculate IB. So generally IC, we know that IC is equal to beta times of IB. Now if you want to find out this IB, then you can define IBC by beta. It should be defined in terms of Q point parameters, hence IBQ is equal to ICQ by beta. So hence the ICQ value is 1 milliampere and the beta value is 100, then IBQ value is 10 microamperes. Then we need to calculate the base resistance. Means if you observe this base resistance, then apply the KVL at the input side. So means the potential between VCC and internally this contains a VBE on voltage by your IB value. So hence VCC minus VBE by IB value, or means V by I. So hence VCC is 10, VBE on is 0.7, IBQ we observe the 10 microamperes. then the RB value is 0.93 mega ohms. Now we'll discuss the part B questions from this module too. So explain the various current components in an NPN bipolar junction transistor within a diagram. So to attempt this question, first you need to understand. First you draw this the NPN transistor construction, and then how what the currents are flowing means it allows the base current, emitter current, and collector current. Then you can indicate with the flow of current directions. Then you can explain the operation of that NPN bipolar junction transistor. And if you want, you can refer this the construction of the transistor video. Now define the current gain parameters of a common emitter, common base, and a common collector transistor, and relate the parameters. So we know that the current gain or any gain. So gain is always defined as the ratio of output parameter to the input parameter. So here we are going to define the current gain, that is equal to output current to the input current. So coming here in a common emitter, the common emitter is defined as a DC current gain is defined as a beta. So means the output current, common emitter means the collector current is the output current and input current is beta. So IB, base current. So hence for this is CE configuration. The beta is defined as the current is defined as IC by I. Similarly for a CB, so it is defined as alpha, means it is the ratio output current. CB means output current is a collector current and the input current is a emitter current. Hence alpha is represented as IC by I. Similarly, for a common collector, it is the DC current again is defined as gamma, means again the output current in common collector means output current is a emitter current and input current is a base current. Then if you want to relate this formula, alpha is equal to beta by 1 plus beta, or you can write beta in terms of alpha by 1 minus alpha. If you want to write this gamma, 1 by 1 minus alpha, or you can write 1 plus beta. So these are the relationship between the three parameters. You can explain this for this way. Now demonstrate the working of transistor in common emitter configuration and draw its input and output. So for this case, first you draw the transistor configuration under the common emitter mode. Then apply the proper biasing conditions for input side and output side. Then you can explain the characteristics with respect to input and the output. Means while explain the input characteristic, should maintain the output should be constant. And then while explain the output characteristic, you should maintain the input should be means input base current, input current should be constant. Then plot the output characteristics. Then if you want, you can refer this CE configuration with the characteristics video. Now, similar to that, another question is explain the working of transistor in a common base configurations and draw its input and output characters. So for this question also, first you draw the common base configuration construction, then apply the proper biasing input side and output side, then explain the operation with the characteristics, that is input characteristics and output characteristics. Then for this case, you refer this common base configuration with input and output characteristics video. Now another one is explain the working of a transistor in a common collector configuration and draw the input and output. So for this case, you first draw the construction of common collector, then apply the proper biasing, then you can explain with the input and output characteristics. Means in any case, the input characteristics are drawn between the input parameter, means input voltage and the input current. While drawing the output characteristics, we need to plot the characteristics between output parameters, that is output voltage and output current. Then you can refer for this case, you refer this common collector configuration with the characteristics video. Now show the H parameters of a bipolar junction transistor in a small signal model. So we know that the transistor is acts as a two-port network. So means the input side it contains the two ports, two parameter the physical quantities are measured in terms of input current and input voltage, and similarly the output side also we are measuring in terms of two physical parameters, that is output current and output voltage. Out of these four parameters, we need to define the two dependent parameters, or those represented independent parameters here. So hence, from this, the input voltage and the output current are the dependent parameters. Those to be represented in terms of small signal model or H model, and we know that the V1 is represented as Hi times of I1 plus HR times of V2, and I2 is represented as HF times of I1 plus HO times of V2, where HI, so this HR, HF and HO, these are H parameters. So based on that, this is an equivalent small signal model. So we are writing this V1. V1 is equal to HI times of I1 plus HR times of V2. Similarly, the output side, the collector I2 is represented as HF times of this one current, so HF times of I1 plus H4 times of V2, where HI is nothing but input impedance, HR is a reverse voltage gain, HF is a forward current gain, HO is output admittance. So we need to define these four parameters with respect to the configuration. So we have three types of configuration: common emitter, common base, common collector. For every configuration, you should define these four H parameters: input impedance, reverse voltage gain, forward current gain, and output admittance. The next question is define active region and connect PNP and NPN transistors in a active region. So for this case, we have the four modes of operations, and based on the transistor construction, we have the two junctions. One is emitter base junction, another one is a collector base junction. If both the junctions are reverse bias, then the mode of region we can say that cutoff region. If both the junctions are forward bias, then we can say that saturation region. Then when emitter base junction is a forward bias and the collector base junction is a reverse bias, we can say that that is active region. And when emitter is a reverse, collector base a forward, that is called as a reverse active region. So for this case, now we need to connect the PNP and NPN transistor in a active region. Let us consider if it is a PNP transistor, and most of the cases for amplifiers we are going to prefer common emitter configuration. So hence, let us take if it is a PNP transistor, this is a P, N and P type. Let us take this base, and this is collector, and this is emitter. Now we need to define in a active region here. So for this case, so how to make this is active region? So based on the principle of this one, we know that the emitter base junction is forward bias, means this is forward bias means, and the base is read with N type. So hence N should be connected with a negative probability with respect to the common terminal. And this is now this input junction becomes forward bias. Similarly, to satisfy this active region, the output junction should be reverse bias, means on the output side we have the collector terminal. The collector is made up with a P type, hence so in reverse bias means P should be connected to negative pole. Then with respect to this one, then it becomes this output junction becomes reverse bias. Hence This given configuration that here the transistor is acts as a active region for this is PN. Similarly, if you want to draw with a NPN transistor, let us consider this is NPN transistor, base, collector, and emitter. So for this case, now I'm going to take this is N and the PN. So the base is made up with a p-type material, hence P is to now we need to make the forward bias. So here we are going to make the forward bias when P is connected to positive to the battery. With respect to cathode, we can say that a particular PN junction is forward bias. So otherwise we can say that it is reverse bias. Hence P is connected to positive pole of the battery with respect to this emitter, and this is represented as the VPP. And similarly, output side, the collector is made up with N type. Now we need to make the reverse bias, means N is connected to positive pole with respect to this one, and this is VCC. Now here, this due to this one, it is acts as a reverse bias, and due to this it is forward bias. And from these two configurations, this is PNP transistor and the NPN transistor, both are acts in a active region. Now the next question is, the transistor has IE is a 10 milliamperes and alpha is a 0.98. Now we need to find the values of IC and IB. So from this we know that I alpha is equal to the ratio of output current to the input current. The input current is IE. For this, this is for okay. Then if it's a common base, we know that emitter is input and collector is output. So hence, in that common base configuration, I assume the base on the given species the ratio of output current to the input current. So here, and we need to calculate the IC. So here IC is an unknown parameter, but we know this know I alpha as well as IE. So hence alpha value is 0.98, that is equal to IC by IE is 10 milliamperes. So 10 into 10 to the power of minus 3. Then you can, by using this ratio, you can solve this IC. It produces a new IC value. After this, we need to calculate the base current IB. So now we know the summation of emitter current and collector current. So hence IB is equal to. So generally we know that I is equal to IB plus IC. So hence IB is equal to IE minus IC. So hence here the IB is equal to the potential difference between the emitter current and the collector current. So here IE value is, what is IE value they given? 10 milliamperes minus. So how much IC we got, that should be substitute here to observe the base current, that is IB value. Now determine the H parameters from the common emitter configuration using NPN transistor. So for this case, so we know that H parameters, that is HI, HR, HF and H4. So for this common emitter, N is between HIE, HRE, HFE and HFE. So we know that input impedance means for this common emitter, so this is input parameter, and across the collector we are going to measure the output, but internet contains some saturated voltages, that is represented as VCE SAT. So this HIE, or it is also called as the ZI, it is the ratio of input voltage to the input current. So what is the input voltage here? The input voltage is passing through the base, hence that is represented as VBE by your means, if you are like the potential difference also here. Then again now input current is the input current is IB here. So hence the HI is represented as VBE by I. So reverse voltage gain means it is the ratio of input voltage to the output voltage. So V input voltage means here that is equal to VB by VC sat. Forward current gain, that is means is the ratio of output current to the input current. What is the output current from the common emitter configuration? The output current is, so emitter current is output IE by, then the input current is base current, that is IB. So hence HIP is equal to the ratio of input current to the emitter current to the base current. Output admittance HO is equal to 1 by Z naught and 1 by R, otherwise you can write 1 by R naught. So what is the Z naught? Is the ratio of output voltage to the output current. So means output voltage to the output current. What is the output voltage? That is VC sat by output current is IC milliamperes here. Then you can solve this one, you can substitute in this ratio, then you can find out this HOE, output admittance parameter. Now define the cutoff region and connect PNP and NPN transistors in cutoff. Means cutoff region means just now we discussed that if emitter base junction is a reverse bias and the collector base junction is a reverse bias, then we can say that the particular transistor acts as a cutoff region. Now you can connect the PNP transistor and the NPN transistors in a cutoff region. Means let us take, suppose if I given this is NPN transistor, this is NPN. Now input should be in a cutoff region. So what is input cutoff region? Means emitter base junction should be reverse bias. This is P means base material. So P means now we need to make the reverse bias to satisfy this cutoff region. Reverse bias means how to make the reverse bias. So means this P should be connected to negative pole with respect to the positive. Now this is due to this approaching of the bias, the input junction is becomes a reverse bias. Similarly, to make this cutoff region, output should also be made to make the reverse bias. Means this is N type. So N means you should be up to positive. Then again a negative polarity is connected to the common terminal. And due to approach of this voltage, the output side, this particular junction is acts as a reverse bias. Hence, from this configuration, both the junctions are reverse bias, hence it acts as a cutoff state. Now explain the DC and AC tolerance of BJT. Means to identify the proper Q point, then we need to analyze with respect to DC conditions and AC conditions. So for complete information, you should refer this DC and low layer analysis of the BJT video session. Then in a common base connection, the emitter current is I is 6.28 milliamperes and the collector current IC is 7. Then find the common base DC current gain. So common base DC current gain means is the alpha DC. So it is the ratio of output current to the input. Output current is IC by input current is I. So hence, from the given question for the common base configuration, IC value is 6.2 milliamperes. 6.2 into 10 to the power of minus 3 divided by the IE value is 6.28 into 10 to the power of minus 3. Then you can solve this ratio, it gives the alpha value. The next question is, if a transistor has a value of alpha is 0.97 and then we need to calculate the beta. And similar to that, this is the first case. In second case, if a beta is a 200, then find the alpha. So here, now we know that in the first statement, we know that beta, to identify the beta, only the known parameter is alpha. So hence, we need to write this beta in terms of alpha. Beta is equal to alpha by 1 minus alpha. So alpha is 0.97 minus 1 minus 0.9997. To solve this ratio, then you can use that beta value. Similar to that, another approach is they given that beta is a 200. So in this case, we need to calculate alpha. So beta means what is the beta? It is a ratio of collector current to the emitter current. So what is the value we observed over here? So for this case, to find the value, to identify this one, so here we need to calculate the for this case, we will calculate the alpha. Alpha is equal to beta by 1 minus, so this is 1 plus beta. Alpha is in terms of beta, so alpha is equal to beta by 1 plus. So here beta value is 200. 200 by 1 plus 200 means 200 by 200 that is equal to approximately 0.99 volts. That is second case. Now, then the question is, a transistor has beta is 100. If the collector current is 40 milliamp, means the beta is the DC current again is 100, and the collector current IC is a 40 milliamperes. Then find the value of IE. So we need to calculate IE value. So for this case, we know that IC is equal to beta times of. So generally, can write IC is equal to beta times of IB plus 1 plus beta times of IC naught. And from the transistor principle of operation, the reverse saturation current is very, very small compared with the majority charge flow carriers. Hence, here I am going to measure this IC naught. Hence, IC is approximately beta times of IB. So, for this case, now we need to calculate IB. So, how to calculate IB? So, IB is equal to IC by beta. So, what is IC? The IC value is from this we need to take. And now we need to substitute the beta value. So, here the beta value is 200. Then you can observe this, what is the new IB value is required. Now, another question, for a transistor circuit having alpha is 0.98 and reverse saturation current ICBO and IC naught is 5 microamperes and the base current is 100 microamperes. Find the collector current and emitter current. So we know that generally here the IC is represented as alpha times of IE plus IC naught ICBO here. So means for this common days is represented as IC is equal to alpha times of IE plus ICBO. Now from this case, if you want to define this, alpha value is a known parameter, and here again IC is a unknown parameter, IE is also a unknown parameter. Then reverse saturation current is or otherwise we know that alpha is equal to IC by IE. So now again we need to calculate. So IB they given that means, so IE. So first we need to calculate this IC is equal to beta times of IB plus 1 plus beta times of IC naught. So now here beta is unknown parameter but alpha value is there. So hence beta should convert in terms of alpha by 1 minus alpha. Then you can observe the beta value. You can substitute here beta value and IB value is 100 microamperes. Then this 1 plus beta and IC naught. This IC naught value is 5 microamperes. You can solve this all these parameters to observe the IC. After this IC, we can simply calculate IE. So what is IE? IE is equal to IB plus IC. So IB value is observed from statement. IB is 100 microamperes and IC is derived from this one. Now you can observe this IE is equal to IB plus IC. So up to this point in this session, we observed the question bank discussion on a module 2, that is bipolar junction transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.